We're now going to take a look at Chapter 9, Section 4, which is going to be looking at the area of polygons and circles. So with polygons, we're mostly going to be talking about parallelograms, trapezoids, and triangles. And we're going to be able to find the area of each of those shapes utilizing different formulas. We're also going to be able to find the circumference and area of a circle using that formula. So if we roll back to what the concept of area is, we already know the area of a geometric figure is a measure of the region bounded by its sides. So kind of like the room in a house, it's bounded by the walls, and the area is going to be the space between those places. We also know that area is measured in square units, so something like centimeters squared, inches squared, or square feet. Here's an example of finding an area of a rectangular room. Most rooms that we think about are rectangular by nature, and so in this example, the room measures 8 feet by 10 feet. And we're looking at inserting tiles that are 12 inches on a side. Each tile, because they're 12 inches and 12 by 12 is 1 square foot, takes up exactly 1 square foot because that's the definition of a square foot. So 12 inches is 1 foot, therefore it's 1 times 1 for the area. So if I want to actually sketch this out, this would be the image that's over on the right-hand side. We would have 10 tiles for the row and 8 tiles for the vertical piece. And so I could either count the total number of tiles in that shape, or I could multiply 10 times 8 and I could get that this is 80 square feet. So 2 different ways of approaching the idea of how many tiles are needed, as well as, or how many square feet are needed. So if I need 80 square feet in tiles, I want to take that and go, how many of those do I need? So if each tile is 1 square foot, in this unique case, you would need 80 tiles. So it's not always going to work out that your area is the same as the number of tiles that you need. That is unique to this problem because we had 1 square foot. There's nothing about the 10 and the 8 feet here. No matter what your length and your width are, you're going to have different dimensions of rows and columns. So the formula for the area of a rectangle is length times width. The formula for the area of a square is side squared. Now, what's important to realize is that a square, it has a length and a width, but they're the same. So it's not actually 2 different formulas, but it's a different way of thinking about it because the length and the width have the same value. We call them a side. So in this example, we have this L-shaped room. And at first, it might be a little intimidating because it's an L-shaped room. But if we cut this into 2 shapes where I have 2 different rectangles, so I have a 10 by 10 square basically, and then I have this other rectangle which is going to be 15 by 5 because 15 minus 10 leaves 5 feet left over. And so we're planning to carpet an L-shaped living room. Let's find the cost. Well, I've got the 2 shapes here, and that's helpful because then I can just find the area of each shape as we talked about. So I'm going to do the 15 times the 10 for that larger rectangle. And then for the square, because I'm left with 5 and 5, I'm going to do 5 squared, which is 25. I add those together to get the total amount, and I get 175 square feet. What is tricky here is they gave me the cost not in square feet, but in square yards. So I have to use my unit conversions to convert from yards to feet. So it's in feet, which means feet needs to be in the denominator when I complete the conversion, and I get $486.11. So that's going to be the cost to carpet the room. Once you know the formula for the area of a rectangle, we can actually develop the formulas for area of other polygons utilizing that. So the trick for a parallelogram, is going to be to cut off the extra piece so it turns into a rectangle and a triangle. So we can start to make other shapes by putting together the shapes that we know. And so in this case, you'll see the blue shaded triangle, and then you're going to see the portion of the parallelogram that's not got the triangle. So that gives me the height of the parallelogram, and then the base is the length at the bottom. So therefore, the area of the parallelogram is base times height, but that height is actually calculated from finding that right triangle inside the parallelogram. So if I look at this parallelogram, the 9 inches is not terribly helpful, because the 9 inches is not the entire length there, and then we have the 8-inch hypotenuse. And I know that it's 12 inches total. So we're given the base and not the height. So we're going to have to find that information. So this is a bit more of an advanced problem. So in the sequencing of when you're teaching this to your students, you would have found straightforward areas of parallelograms before you ever attempted one that's like this. So we would have the actual base and the height labeled, and they would just be multiplying those together. But for the sake of, your homework within the software, I want to make sure that I look at the slightly tougher problems that really make sure you understand the concepts and not just the simplest version of them. So in order to do this, I'm going to have to use the Pythagorean theorem. So that 8 that they gave me was the hypotenuse of the triangle. And I know that from the shape they're giving me here, that base of this triangle right here is 12 minus 9, which is 3. So I'm going to plug into the Pythagorean theorem and say the height squared plus the side squared, 3 squared, is equal to the hypotenuse squared, which is 8 squared. When I do that, I'm going to do 64 minus 9 equals my h squared. Then I take the square root of both sides. I don't want to necessarily write that as a decimal just yet, because that could be prematurely doing that. Now that we have that, we can actually take the base times the height. Now it's important to remember the base is not the 9. The base is the length of that entire side. So the base is actually 12. So the area here is going to be 12 times the square root of 55, and my units are inches, so they're inches squared. Now, if it wants me to round to the nearest inch, I'm going to type that into my calculator, and I'm going to round according to the decimal. Here's another example with finding the area of a triangle. In this example, we've got the diagram below. And if I make an identical copy of this triangle and flip it upside down and place it on the original, what's that going to look like? So that's a lot of steps, right? And if I do that, I'm basically going to get the sides to match up, and I'm going to have a rectangle. So if I want to find the area of that figure that looks something like a rectangle in terms of the base and the height, and I've got the two figures made up from the addition of the two triangles that I've flipped and oriented differently. So this is kind of what it looks like. You'll see the second figure on the right is going to be what they look like when they're put together. So this looks very similar to our parallelogram, whose area is base times height. And if you think about it, the area of a triangle is 1/2 base times height. So it should make sense if I double that, it would be 2 times 1/2 times base times height. So not only do I get a parallelogram, it's one with the base and a height, which basically proves the area. And it's also found from, like I just said, with taking that 2 times the 1/2 base times height from the triangle. So this is our area formula for a triangle. If I want to find the area of a triangle using that diagram there, it's important to note that the 20 is not involved in the area calculation. The height is actually going to be 5, which is the perpendicular side. So when I do 1/2 the base times the height, that's going to be 1/2 the 11, which is the entire base, times the height, which is 5. So I get 55 over 2. The measurement is in feet, so it's square feet. Now, the formula for the area of a trapezoid, this is one that students have to really remember. This is somewhere they can typically get stuck. It's 1/2 the height times the sum of A and B. So if I look at this example, A and B are 14 and 19. 4.5 is going to be the height. So if I plug this into the formula, I'm going to get 1/2 times 4.5 from what they gave me. And then I'm going to do times the sum of the 14 and 19. That's going to give me the 74.25. The units are feet, so it's going to be in square feet. Now, circles follow a little bit of a different rule than traditional polygons, and they involve a special irrational number of pi. A circle is defined as the set of all points that are matched up to a given radius. So if I took a 1-inch piece of yarn and I spun it in a circle, all those dots that I would draw would connect to form a circle. And the piece that I am using from the yarn as a starting point would be the center of the circle. So based on the center of the circle, there's always this radius idea, and there's also the diameter that I'm utilizing to generate the circle. The radius of the circle is an interesting calculation because it depends upon the diameter as well. So I can take the diameter and divide it by 2 to find the radius, or I can take the radius and double it and find the diameter. What is unique to a circle is that instead of referring to distance, we say circumference. So the circumference is the measurement. If you took your Apple Watch or your Fitbit and you walked around in a circle, it would measure how far you walked as you went around that circle. You could also calculate it by doing pi times the diameter, or 2 times pi times the radius. So here's an example where we're finding the distance around a track. So in this track, I have 2 sections. I have a 300-yard width of the track, and then I also have 700 yards from front to back, basically, from that complete distance. From the diagram, I can see that the diameter of the circle is 300 yards. So the circumference is going to be pi times d, which is pi times 300, or 942 yards. So that is the total length of the curved portion, since the 2 half circles make one full circle. So when we're talking about that, I'm talking about these little curved pieces right here that are arcing in. Because I have 2 curved pieces, that's going to be the amount. Here, if I'm finding the area around the rest of the track, I've got a bit of a rectangle, so I can utilize that piece and do 700 minus 2 times 150, which is going to give me the remaining area around that track. And now I can add it all up together to get the 942 plus 400 plus 400 to get the actual full yards. In this example, we want to find the area enclosed by the track in example 7. So now it's not the length of it, it's the actual area that is enclosed. So in order to do that, I'm going to need to do a few things first. The area would be the sum of the area of the rectangle matched up with the area of the circle on the bookends. Because 2 half circles form one full circle, I'm going to use that same fact again to be able to get to my answer. So the area of my rectangle from the previous calculations is just going to be the length times the width, or 400 times 300. The area of my circle is going to be the radius squared times pi, which would be 150 squared times my pi is approximately 70,650. And so when I combine that, I get 190,650.